Hi everyone, my name is Kulit Vikramasinghe and I'll be doing the discussion for the Physics 1 that you guys would have gotten a few days ago. Okay, so uh, I'll just be going question by question, in the order that is given in the paper, and then I'll be basically explaining to you as to why the correct answer is the correct answer. Okay, so first question. Which of the following statements is true regarding waves? 1. Transverse waves propagate with compression and refractions. 2. The distance between a crest and a trough of a transverse wave is equal to the wavelength of that wave. 3. It is not necessary to have a medium of propagation. 4. Energy is transmitted by mechanical waves without the transmission of substance. Okay, so let's go through this answer by answer. So the first question basically says that transverse waves propagate via compression and refraction. So this is a relatively theory-heavy question. This is just something that you kind of memorize as you do more and more of these questions and past papers. And you've probably been taught that this is false. Compression and refraction are properties of longitudinal waves, and this one says that it's properties of transverse waves. So that is not the case. That is those are features that you generally see in longitudinal waves. Okay, second one, the distance between a crest and a trough of a transverse wave is equal to the wavelength of that wave. Alright, so I'll just draw this one out for you so that you can ideally memorize this in a more convenient. Okay, so this is basically your wavelength, right? So, okay, you know what, let me just expand that further. Okay, I think that this pen is running out. But yeah, basically, you have these ones are called crests, right? Okay, hold on, let me just pull it down. So yeah, so these ones are called crests, these ones are called troughs, basically. So what this question says is that, or what this option says, is that the distance between a crest and a trough of a wave of a transverse wave is equal to the wavelength of that wave. So what that's saying is that this distance is equal to a wavelength. But we know that that's not true. Why? Because a wavelength is defined as the distance from a crest to a crest, or from a trough to a trough. So basically, what this distance here represents is half of a wavelength, so that option then is wrong. Third option, it is not necessary to have a medium of propagation for mechanical waves. This one, again, it's a relatively theory-heavy option, and basically that's wrong, because at the end of the day, for a mechanical waves are waves that require some form of medium, right? Whether that be air, whether that be water, whether that be a solid object, you need some particles to vibrate for this kind of mechanical wave to travel through it. So that third option is wrong. And then finally, fourth answer. Energy is transmitted by mechanical waves without the transmission of substance. Okay, so even if you didn't know whether this one is correct or incorrect, because you've already eliminated the first three, you should be able to get this fourth option as correct. But again, the fourth one is just another very theory-based question. Energy is transmitted by mechanical waves without the transmission of substance. Yeah, that's correct, right? You don't need the transmission of substance for a mechanical wave to actually go through or move that, right? So basically then, that fourth option becomes your correct answer. So the answer for question 1 is number 4. Question 2. Consider the instances A, B, and C below. A. A bat flying at night emitting ultrasound waves of 21,000 Hz. B. A dolphin praying in the ocean emitting ultrasound waves of 21,000 Hz. C. A rabbit walking in the jungle emitting ultrasound waves of 21,000 Hz. If the speeds emitted at the above instances are VA, VB, and VC, which of the following relationships are correct? Okay, so what they've done here is kind of mislead you in a way, where they've given you, okay, fine, sounds moves with like, or like each of these sounds has the exact same frequency by giving you like 21,000 hertz for all three of them. And they've basically said, okay, now figure out which one travels the fastest. So the thing here is, the speed that a certain wave travels at is completely independent, or does not depend on what the frequency or what the pitch of that certain sound is. So then what exactly does it? In this case, the one thing that changes from like each of these instances from between A, B, and C is the medium that it's in, right? A is a bat, you know, it's just flying in the air. So through what medium is like this sound going through? It goes through air. It goes through just the regular atmosphere that we have. B, where a dolphin is like, you know, in the ocean. In that case, the sound doesn't travel through air here, right? Because the dolphin is underwater. So where does it go through? It goes through water. And we know, like this is taught to you guys for like 2 or so years at this point, that sound travels faster in water than it does in air. So you know that automatically the sound emitted by B, or like in instance B, is going to be faster than the sound emitted in instance A. And then instance C, again, it's just like instance A, right? It's just a rabbit, you know, the sound travels through the air. So basically what you then know is that in A and C, sound travels through air, whereas in B, it travels through water. So then in A and C, your speed, or like, you know, the velocity, or the speed here is going to be the exact same for both A and C, and there's 2 options like that, which is 3 and 4. But you also know that the sound emitted in instance B is going to be faster because it travels through water as a medium. So then speed B is just going to be higher than VA and VC. So then that only leaves option number 3, because VA and VC are going to be equal, and VB is going to be higher than both VA and VC. VA and VC. So your answer becomes option number 3. Okay, third question then. The sound wave obtained by tapping a drum softly was observed in the cathode ray oscilloscope as in figure A. Which of the following could be the waveform that is obtained when the drum is tapped with a larger force than the above instance? So in this case, just think that you have a drum, right? You tap it, a certain sound comes out, and then you tap it with a larger force. That means you just hit it harder, basically. So in that case, what exactly happens? The drum is going to make a louder noise, right? The drum's pitch isn't going to change, the velocity, like, you know, all that's irrelevant, because the one big change that you will notice when you hit a drum harder is obviously that the drum's just going to make a louder noise, right? And we know one thing, or like the one loudness, or like what we perceive as loudness of a certain sound, is the amplitude of that sound wave. So what an amplitude is, you know, basically if you have this as your sound wave, this height is your amplitude, right? So basically then, what you're going to want to look for is an answer where this amplitude, or like this height, is larger than that given in figure A. Okay, wait, let me just redraw this diagram actually, because I think that it's not particularly clear. Wait. Okay, I think this is better, right? So this here is the is a figure in which this value, or like this height, is larger than the height given in figure A. So, okay, I'll be honest, in this question we do have a bit of an issue, because basically 2 and 4, it looks like the amplitude has gotten bigger. So even in the past paper, like, you know, even in previous O-level papers, or like this, for this specific question, which was given in 2019, the answer for this was all, and a mark was awarded for everything, because the diagram in this specific question is a bit unclear, because 1, 2, and 4 all have higher amplitudes, and you cannot tell for certain like which one of these three answers would then be correct. So basically, for this specific question, it is going to be all, but just keep in mind when you hit something and when a louder sound is made, what you want to look for is an increase in this amplitude. Okay, so moving on. Question number 4. When a sound wave emitted out through air, and then you've got 4 options. 1. Frequency decreases. 2. Velocity increases. 3. Wavelength increases. 4. Amplitude decreases. Okay, so again, with a lot of these physics questions, I feel like you can just think about what happens in real life and then go along with that, right? As long as you like some very basic things. So what you use for this question is the exact same thing that I just discussed previously, right? The louder a sound is, the higher its amplitude is. So what this question is talking about is basically where a sound is and it travels through the air. So if I'm standing on this side of the room and then you are standing on the other side of the room, when I shout, what you will notice is that as you get further and further, as you get further and further away from me, the sound of me shouting is low, right? Basically what that means is travels through, loudness decreases. And like I explained in question number 3, what does a decrease in loudness means? What does a decrease in loudness mean? It basically means that the amplitude is reducing. As the sound travels further and further in air, that loudness or that amplitude decreases. You actually learn more about this if you just pursue levels, basically where the energy is proportional to the square of the amplitude, but that's more advanced stuff. But for now, what you just have to remember is the very basic stuff. As you get further, the loudness or the amplitude reduces because as it travels through air, that whole thing is lowered. Okay, so then the answer becomes option number 4. Okay, 5th question. The situation of transverse wave traveling on the surface of water at a certain moment is shown in the figure. The amplitude and the wavelength of this wave respectively are. Okay, so we've been given a diagram in this for everyone's convenience. Right, so hold up. And this is 5. Okay, so this diagram continues towards the right side, but just for now, this is information that what are you're told that okay, this height here is 4 centimeters and this length is centimeters, and what it's asking you for is the amplitude and the wavelength. Okay, so this is the 3rd time that we're discussing this amplitude thing, and I keep on redrawing the exact same diagram, unfortunately. But basically, you already know this. I explained this 3 times. Well, this is the 3rd time. This here is going to be your amplitude, right? So this 4 centimeters is going to be your amplitude. Now, I think in the first question, I basically explained that your wavelength is going to be the distance from a crest to a crest. So let's just draw another crest here. From a crest to a crest, or from a trough to a hypothetical trough here, right? But basically any distance that makes up that, or that is equal to that, is considered the wavelength, right? So here, what you will notice then is the distance from this, or from this peak to this peak, so from this crest to this crest, is always going to be equal to, or in an ideal scenario, it is going to be equal to the distance from this beginning point to this end point, right? So basically it goes up and comes down and goes back to its starting position. This distance is going to be equal to this distance, right? So this whole thing, or this distance here, can be considered a wavelength. What you've been given then is this. You've been given that this is 5 centimeters, and because this section and this section are identical, you can say that this one, or like this distance here, is also going to be 5 centimeters. So then what do? You add this distance and add this distance, and you have this entire distance now. So this whole thing, or like this whole distance then, becomes 10 centimeters long. Your wavelength is a 10 centimeter wavelength. So what are the options here? You've got 4 and 5 centimeters. That's wrong because we know that our wavelength is 10 centimeters. You've got 4 and 10 centimeters. That is the prime candidate for the correct option right now. You've got 5 and 4 centimeters. That's wrong because we know that our amplitude is 4. You've got 8 and 10 centimeters. Again, wrong because amplitude is 4. So here then your only option really becomes option number 2, which is 4 and 10 centimeters. So the answer is answer 2. Okay, so let me just erase this. Question number 6 then. Consider the following statements given about mechanical waves. A. The frequency of changes on entering from one. The frequency of the wave changes on entering from one medium to another. B. The speed of the wave does not depend on its frequency. C. The speed of the wave depends on the medium through which it travels. Of the above statements, which is/are true? Okay, so what are the options here? First one, frequency of a wave changes from sorry, I lost this. Okay, from entering one medium into another. So what that basically means is that this option says that, okay, if I go from, or like if a sound wave travels from air to water, that suddenly the frequency changes. Okay, so this one, I guess, isn't going to be something that you can just like guess off of what you see in real life, because, you know, it's hard to tell whether, like, you know, it's hard to practically think whether frequency changes once it like goes from air to water, right? But this is like one of those easier things to remember, and you will come across this in as well. But basically, no matter what kind of medium change happens, your frequency will always stay the same, right? Your other stuff might change, as long as, you know, even if it travels from like one medium to another, it will remain consistent. It will always be the same. So that first statement then is completely false. B. The speed of the wave does not depend on the frequency. Yeah, that's true, right? Because, okay, so there's two ways to get this. First, it's just you knowing this, right? You know, if you know the theory, you know that the speed does not depend on the frequency. Those are two completely different, or like completely, yeah, they're unrelated qualities. But if you can't remember it like that, another way that you can get this is that if, like A, we just discussed that frequency is always the same, and you know for a fact that, like, even in our previous questions we discussed that, like, speed changes when you go from medium to medium, like speed, or like the speed of a wave is fast in air, is fast in water than it is in air. Then basically you can just deduce if speed changes with the medium, but frequency does not change with the medium, then the speed does not depend on the frequency, right? Because if speed depended on the frequency, if frequency stayed the same, then speed should probably stay the same, right? It's not a perfect way to remember it, but, like, you know, if you want, you can kind of remember that vice versa, right? But yeah, in general, what I would suggest is definitely, you know, these are two completely different properties, right? That's like saying, you know, okay, a cube depends on, like, its color, right? Or like the shape of something depends on its color. It doesn't, right? They're two completely different things. Okay. C. The speed of a wave depends on the medium through which it travels. This is true, right? Like, I feel like a lot of people into O levels, what you will generally notice is that things, or like waves or solid medium, they do through the air. Okay, so then what do you have? You have your first option is false, your second option is true, your third option is true. So your answer then becomes answer number 4. Yeah, only B and C. Okay, Question number 7. So here, we're switching from, this previous one was waves and oscillations, right? Yeah, sorry, waves and their applications, and now we're switching to friction. Okay, so what's this question here? Alright, the figure shows how a horizontal force, P, is applied on an object and placed on an object placed on a plane. When the figure of P is gradually increased from 0, the frictional force F on the object. Okay, so for this I feel like, this is extremely important, and like, especially like this part about like friction and like all that, like it's very important if you want to pursue like physics for your A levels, so memorize this or like, study this properly, right? Okay, so what exactly happens here? You're told that there is a big block, just okay, I'm just gonna draw this out as well. Nope, that's not working. That's fine. So basically, there's a block, right? And this block is basically being pushed by a force P, and there's a frictional force F acting here. Okay, so what exactly does this mean? Just imagine that there's a massive block here. It's like a massive metal block. It's really heavy, or like think of a wooden crate or just something heavy, right? So what is the force P then? The force P is whatever external or like outside force is being applied on it, right? Think I try to push the box, right? And that is basically going to be the force P. But the thing is, just because I push the box, it doesn't suddenly move, right? Like, if I'm just like slightly, like just very barely pushing it, then the box isn't going to move, right? Now, we generally say, or like, we generally think, okay, that's because this box is really heavy, that's why I can't push it. But really, that's not what's happening here, right? What's happening here is that there's another force acting opposite to the force that I'm applying on the box, right? So when I push it this way, there's something else pushing back against what I'm doing. That force is friction. So we have an equation for friction, which is F equals mu r, right? So let's make that mu r. So, I mean, you don't really, yeah, basically what this is the force acting downwards by the weight, right? Because everything, like anything, like just this eraser, for example, right? There's a weight acting down, right? Like, when I throw it up in there, it comes down because the weight, or basically what you call butter, acts down, right? So basically then what happens is that downwards force times a certain value, right? This mu thing, don't think of like mu too hard, because really mu is just a number, right? Basically mu is just a hypothetical number, or like, it's just a number to kind of simplify, this entire process, right? Basically, what you will see is that, like, if you are working with ice, like, if the floor is ice and like I've got a big wooden box on top of the ice, I can push that very easily, right? That's because mu is very low, right? Because basically think of mu as like how good a certain like interaction, or like how good a certain two surfaces are at creating friction, right? So the higher mu is, the more friction can be generated, or like the more opposing force can be generated by that, surface on the ground. So yeah, basically, you probably already learned that, to be honest. But what's important here is, this idea of like how exactly your friction changes, right? So just keep this in mind. Basically, this is a big box. I'm pushing the big box, and there's a friction acting against it. So we've got 4 options, right? 1, it takes a constant value continuously from the beginning. 2, it increases gradually from 0 to a maximum value. 3, it increases gradually from 0 to a maximum value, then decreases gradually. 4, it increases gradually from 0 to a maximum value, then decreases slightly, and takes a constant value. Okay, so what are the options here? you know, think of it like this. If I've got like this big box that I'm trying to push, and I first, like, ever so slightly just tap it with my finger, is it gonna move? Is it gonna, like, move just because I do that? No, right? If I push slightly harder, will it move? Probably. Right? It's a really heavy box. Just me doing this isn't gonna suddenly make it fly away, right? I've got to put a lot of force into it, or like I've got to put a lot of effort into it to make it move. But then, if the box didn't move in both instances, as in, like, when I just slightly tapped it and when I kind of gave it a bit of a push, if it didn't move in both those instances, what that means is that first, the friction was enough to resist just my finger push, and second, it was also big enough to resist that bigger shove. But the thing is, if I'm exerting 4 newtons this way with my finger, and for the box to stay in the same place, the friction has to be the same, right? That means that if I'm putting 4 newtons this way, the box has to put 4 newtons this way as well. So therefore, when I'm applying it with my finger, when I'm applying 4 newtons, it will give 4 newtons back. But when I'm pushing like slightly harder and giving it 8 newtons, if it's still in the same place, then it's got to give 8 newtons back, right? So what that means is that as I push harder, it gives a higher value back. Or, like, the friction increases the more I push. The reason for this is that basically, if you just gave it a slight finger tap, and it suddenly, gave the 8 newtons this way that it would give when I a harder shove, is the box would automatically come this way. That doesn't make sense, right? When have you ever like tried to like slightly nudge something forward and then it just propel backwards? That's not how it works. So basically what you want to keep in mind is that friction is a resistive force. And basically it can never exceed the force that is being, given in the opposite direction to it. So what I basically mean is that if I am like slightly tapping a box, even though it doesn't move, it's never going to move this way, right? If I'm pushing it this way, it's never going to move this way. That's because force in this direction. What it can do, though, is give a lower force, right? So basically, when I like give a very, very hard push, and if I'm like, putting a lot of force into it, then the friction isn't going to be enough to, keep up with that push. That friction is going to give up, and it's basically just going to start moving. So I think I basically just explained friction from like the very bottom there. But basically, what you have is this kind of a graph, basically. Alright? And the way that it works is, so this is the friction, right? So let's just call that Fr. And this is the force. Let's call that P or something. So as I give more and more force, that friction increases and increases, right? This is supposed to be a straight line, by the way. It increases and increases. Then at a certain point, like when I get to that point that the friction cannot resist, it suddenly drops down and just becomes like a very constant value, right? So then, which one of these options best describes that, right? This increases gradually from 0 and comes to a maximum value. Then it decreases slightly and takes a constant value. That is exactly what is described in answer number 4. So the answer to this 7th question then becomes number 4. Okay, so next question then. So there's only one friction question. In this particular, there are probably going to be some more, or like, other force-related questions in physics 2 and 3. Okay, 8th question then. The focal length of a mirror is 30 centimeters. When an object is kept on the principal axis of the mirror, the image formed by the mirror is real and its size is equal to the size of the object. The distance from the mirror to the object is. Okay, so this one, it's like an optics question basically, and to be honest, like with, at least for O levels, what you can generally do is you can kind of just get past these questions by kind of like remembering how each particular mirror works, right? So for a mirror to form a real image of which is the same size the object has to be placed like at a certain place of a concave mirror, right? So a concave mirror, like in case anyone is unfamiliar, is this kind of mirror, right? This is the reflective surface, this is the reflective surface. So in these kinds of mirrors, there's only one instance where a real image can be formed that is the same size as the object. And that is when the object is placed at the center of curvature of the concave mirror, right? And what have you been given here? You're told that the focal length of the mirror is 30 centimeters, right? Focal length is basically half the distance of the center of curvature. So if the focal length is 30 centimeters, the center of curvature is 60 centimeters from it, right? So if this is focal length, this, that's what it's called, right? Yeah, if this is the focal length, then this is going to be the center of curvature, right? So if this is x centimeters, this is also going to be x centimeters. Here we're told that the focal length isn't x, rather it's 30. I is also going to be 30. And what it's asked is the distance from the mirror to the object is. If we know that the object then is at the center of curvature, we know that it is this distance away from the mirror. What is 30 plus 30? It's 60 centimeters. So we know for a fact then that the object is going to be sitting at 60 centimeters from the mirror. The answer is 2. Okay. Number 9. A situation where an image of a flower pot is taken onto a white vertical plane using an item called X is shown in the figure. Which of the following could be X? 1. A plane mirror. 2. A convex mirror. 3. A concave lens. 4. A convex lens. Okay, so again, this is basically another instance where you just have to like know exactly, or like know how these mirrors and lenses and all that work. Alright, so what have you been given? We're told that an image of a flower pot is taken onto a white vertical plane using an item as shown in the figure. Okay, so if this image has been taken onto a vertical plane, or like, you know, onto like a screen basically, what does that mean? Well, one thing for certain, that's that it's a real image, right? Keep in mind that's like a great way to like identify these kinds of, or like identify answers. It's basically that like as long as a image can be taken onto a plane, it is real. If an image cannot be taken onto a plane, it is imaginary, right? I think that's the word. But yeah, basically real image is the only kind that can be taken onto, sorry, virtual, not imaginary, virtual image, right? But a real image has to be a real image because it has been taken. Now, if you look at the diagram given the paper itself, or like the tute itself, what you'll notice is that the flower pot is image generated here is a real, right? So let's look through the options here. 1. Plane mirror. Okay, I feel like 1 and 2 can both be taken out instantly, right? Because if I have like an object, let's just say that it's a candle here, and then like, you know, I've got like a mirror, doesn't matter if it's like a normal mirror, doesn't matter if it's like a convex, it doesn't matter if it's concave, whatever. Regardless of like what kind of mirror is here, in no world am I gonna get an image onto this screen, right? Because we've all seen how mirrors work, right? Just you've got something like behind the mirror doesn't mean that like, you know, this object appears in that like screen behind the mirror, right? What the mirror does is it takes this light and it reflects it the same way that it came from, right? So obviously those first two options are instantly going to be wrong. Okay, so then what are the other options? A concave lens and a convex lens. So here, again, this is just going to have to be like, you know, listen, you could realistically diagrams and like, you know, do all that stuff if you know, have learned how to do that. But again, in these, like for O levels at least, because you've only got a limited amount of like mirrors and like lenses and all that, it's just easier to like remember like specific stuff about them, right? And in this case what you use is the fact that only convex lenses can make real inverted images for for a real object, right? I just drill that into your head, right? Only convex lens images for real objects, all right? It's as simple as that. You like remember that, then this is a very easy question, and you just straight away put answer number 4. So the answer here is option 4. Okay, question number 10. In the following figure, A, B, and C are 3 beams of light using a glass lens. Using a glass lens, one of these beams can be converted into another type of beam that is shown in the diagram. Which of the following correctly indicates this conversion? Okay, so let's look through each of these options, because I feel like this is a process elimination kind of thing, right? You have to go through every single one of them. I mean, generally, yeah, you go through each of them and be like, this one's correct, this one's wrong, this one's correct, this one's wrong. Okay, so A to B. A is just these kinds of parallel lines. B is, you know, these converging light rays, basically. And they say that A to B using a convex lens. Okay, so a convex lens is a lens like this. So, I mean, you just remember like another name that we call a convex lens. This is like relatively easy to do, right? Convex lenses are also called converging lenses, right? Convex, converging, you know, the words sound similar as well, right? So then, what is this doing? What converging means, like for anyone that doesn't know like the meaning of the actual word itself, converging means you kind of bring them closer together, right? You close it basically. And what's happened here, you've taken these parallel lines and you've basically brought them closer together. You've converged them. So what the first option basically says that a convex lens, a converging lens, converges these lines into this. Sounds pretty correct, right? So my bet would be that that one is probably going to be our correct answer. You know, just in case, let's go through the other options as well. Okay, second option, A to B using a concave lens. So that means you have like that same set of rays, and then you take that concave lens and you turn it into this. This is incorrect, right? Why? Because this is a concave lens, right? What a concave lens does by nature is it takes whatever lines you give it and it generally tries to like spread them apart, right? It basically tries to, you know, make them go as away from each other as possible. These lines are coming close together. That isn't what it does. What it would do is it takes these lines and it basically makes them move as far apart as possible, right? So clearly then option number 2 is going to be wrong. Okay, option number 3, B to A using a convex lens. Alright, this one also doesn't make sense, right? Because you've got already converging lines, and then it says that the lens that's called a converging lens, a lens that is meant to make things like come closer together, is somehow turning it into this. That doesn't make sense, right? And generally what you will have is, you know, like this, even the diagram itself looks pretty incorrect, right? So you will not find a set of converging lines that suddenly get turned into like parallel ones, right? I think realistically the only like closest thing that you could do is maybe like this, but even this is wrong because again, this is a converging lens, right? What this would realistically do is take these 3 lines that are going like that and then bring them even closer together, right? Like this, right? That's what it would do. It wouldn't just like, you know, suddenly spread them apart. That's not what a converging lens does. Okay, C to A using a concave lens. Okay, again, this one is C is like this, you know, a bunch of diverging rays, and then this lens would turn it into this. Okay, again, this is wrong because that's what a convex lens does, right? A concave lens, what it does is spread them apart. So if anything, what it would do is take these 3 lines or like these 3 rays and then suddenly, you know, make them go even crazier and like even further apart like this, right? So basically, I mean, from the very get-go, we kind of knew that option number 1 was going to be correct because, you know, the ray diagram did work out for that. But if you wanted to see why the other ones were wrong, that's why I did that one. So yeah, basically, your answer for the 10th question is going to... Okay. 11. Consider an instance where a convex lens is used to read a label with very small letters. Here the label should be placed. So, this is basically just like a magnifying glass, right? If you've, you know, been to your science labs, maybe you have like one at home, like a toy one or something. But basically, this is a magnifying glass, right? What that means is that it's a convex lens. You look through it and you see the small letters as bigger. Okay, the options are given as: it should be between the lens and the focus. It should be on the focus of the lens. It should be on a point which is away from the lens twice its focal length, on a point which is away from the lens more than twice its focal length. Okay, again, this is like a very just like another theory-based one, right? Because you don't want to be drawing the entire diagram and, you know, thinking of that. But basically, from the options that you are given here, you know for a fact that the only option that will give you a bigger... Okay, so, okay, let me just explain this better. Basically, if you are going to be able to view this image, basically through your eye and just on like the lens, what that means is that, and like, you know, it's got to be bigger, right? The small letters have to be bigger. So then, what do you know? You know for a fact that this is going to be virtual, right? You know that it's going to be upright, or like, I think the word that you use in O levels is erect. So erect slash upright. I apologize for the bad handwriting. And thirdly, it's going to be, you know, magnified, right? Magnified. Okay, so you've got things that you need to be, right? Like, you know, when you look through a magnifying glass, you know, the going to be bigger, and if the letters are upside down, then, you know, there's no point in, you know, having, right? So what you're going to need to do is you're going to need an upright virtual magnified image. So to get an upright virtual magnified image through a convex lens, there is only one way to get that kind of image, and that is by having that kind of, or like by having the object itself between the lens focus, right? So what that means is that you are going to have the lens itself, you're going to have the focus, you're going to have the center of curvature. Your object basically needs to be between this and this, right? Between the lens and between the lens and the focus. Again, relatively like just a theory-based one. You just kind of have to remember how exactly it is done. Okay then. Question number 12. What is the ray diagram which illustrates the phenomenon of total internal reflection? Okay. When you think of reflection, what do you think of? You think of, like, I think for a majority of people, it's going to be the word mirror, right? Because that's where you see reflection. You see it in a mirror, right? So I think that's like a decent way to like approach this question, and that's that when a complete reflection, when total internal reflection does happen, you're basically going to get a mirror image of whatever is being, or like of whatever is being projected onto like that surface. Okay, so let's look at the options here. All right, let's like eliminate them one by one. Look at option number 4. In option number 4, you have a surface. You know, you have like, you know, this dotted line to represent the perpendicular. You've got your ray that is coming. You call this the incident ray, right? So it's coming at an angle of, this is called theta. I don't know if you guys have that, but basically it's coming at this certain angle, right? And it changes its direction and kind of goes here. Is this a reflection? No, right? Because there's no reflection. It just goes straight through it. It is basically being, sure, maybe it's being refracted, maybe it's like, you know, changing the path of it, But this isn't a reflection. You know, if I'm standing here, if like I'm looking at it, I don't see like this image or like whatever this light ray is coming back towards me. I just see it going further away. That's not reflection. Okay, let's look at option number 3 then. It comes like this and then suddenly it goes along this line. Okay, again, is this reflection? No, because there's no light ray heading back. If I'm looking, so basically in the mirror, what I see is that the light rays from my body bounce on the mirror and come back to my eyes. The light ray, like from whatever, isn't coming back to my eye, right? It's going like in this way, right? You know, it's not coming in my general field of view or whatever, right? So therefore, this third option is also definitely wrong. So then you have 2 remaining options, right? The first and the second. Okay, let's go to in the second one. Yeah, sure, you have a light ray coming like this, but the angle that it's coming at is really different from the angle that it initially went at. Think of like kind of like, you know, a wobbly version of whatever was projected. Think of like, you know, kind of like Bondavecha image. No, right? You expect a perfectly crisp, a perfect reflection of whatever was projected onto the mirror or like onto the glass or whatever you're seeing the reflection in. So here, you're not going to get that perfect mirror image. You're not going to get that perfect reflection, right? Total internal reflection. You aren't going to get that. You're going to get a reflection, yeah, but is it total, or like, yeah, is it total internal reflection? No, it's not. So then that only leaves really option number 1, right? And even if you kind of went into like this exam not knowing what total internal reflection was, I feel like most people will probably select this option because you think of reflection. Look, that's the exact copy, right? It's the exact copy mirrored, right? It is a complete reflection of the incident ray, right? So basically, only like clear and obvious answer is gonna be option number. Alright, question number 13. The image of a real object produced by a convex mirror is always... This is just another theory one, and I guess you know, as you do more and more of these optics questions, what you realize is that like a lot of the O-level ones are extremely theory based, right? So the image of a real object produced by a convex mirror is always going to be virtual, upright, and smaller than the object, right? I'm pretty sure like in your O-level books, like these are like, given specifically, even if it's not, just like note down stuff like this, right? Because like the object from a convex mirror is always going to be one thing. You probably want to remember that, right? So it's always going to be virtual, upright, and smaller than the object. Your answer is going to be answer number 3. Okay, question number 14. Which is the phenomenon that cannot be explained by total internal reflection? 1. Traveling of light through optical fibers. 2. Making diamonds shiny by cutting and polishing. 3. Formation of rainbows by dispersion of white light into colors. 4. Turning a ray of light by 90 degrees by a rectangular prism. Okay, let's go through this option by option. First option, or like first answer, is traveling of light through optical fibers. For anyone that isn't familiar with like how optical fibers work, but you know, I think a lot of you do know that this is gonna be the correct, or like, you know, this will be correct, or like this will be explained by reflection, because this is like the only example that I remember from like the O-level book. I specifically remember there being like a blue, like an image of like a bunch of blue wires basically for this one. But basically the way that it works is that, you know, light is bounced, it bounces, and like it keeps on bouncing until it comes to its destination. That's how optical fiber works. You know, a expert on the subject, so I can't really explain the full but just keep in mind the way that optical fibers do work is they bounce light through them, right? Okay, answer number 2, making a diamond shiny by cutting and polishing. Okay, so if you look at a diamond, what you will notice is that like they shine like a crazy amount of brightness, right? Like, you know, you will look at it and like you will notice it, right? You drop a diamond on the ground, you will see that. And the reason for that is that it has a tendency to reflect. What it does is it captures the light from like the sun or like a torch or like whatever. It bounces light and basically projects it outwards, and that's how you see that shine in diamonds. Second option, yeah, it can be explained by total internal reflection. Okay, third option, the formation of rainbows, of a rainbow by dispersion of white light into colors. The thing with that is, you aren't realistically gonna have, or like you aren't realistically going to have, like, reflection happening to get to that like rainbow, right? Because just because a white light becomes like a bunch of like other colors, like, you know, red, blue, green, or like whatever, just because that happens doesn't mean that there's any reflection, right? That happens through like this dispersion of light. There's like nothing being reflected here, it's just like being broken up into its core elements. So my best bet right now, the number 3 is the correct option. Answer number 4, turning of a light ray 90 degrees by a rectangular prism. Okay, so I'm not too certain if like you guys have learned how this works, but basically, generally what you will see is, for something to turn by 90 degrees, you are going to need some level, or like, you know, you are going to have some kind of reflection, or like, yeah, basically you're going to have some kind of reflection. It bounces around inside and it comes out, right? You know, that might change depending on what the prism is. Honestly, like, I don't think drawing this is going to be too productive, because how that is shaped affects how it, you know, comes out. To be made, or like, you know, for that angle to deviate so much, you are going to have some kind of reflection, or like, you know, some kind of internal reflection. It's going to bounce around inside, it's going to come outwards. So then, yeah. So then, what are the options here? You've basically only got 3 as the correct option. You know, even if you don't know the other ones, like, clearly light rays splitting up into other light rays doesn't automatically turn it into like a reflective substance or whatever. Your option is gonna, or like your correct answer is gonna be option number 3. Okay, question number 15 then. Okay, this is the force one again. A 4 Newton force and a 3 Newton force are applied on an object at the same instance. Consider the following statements given about the magnitude of the resultant obtainable at that occasion. A. The maximum magnitude of the resultant obtainable is 7 newtons. B. The minimum magnitude of the resultant obtainable. C. The magnitude obtainable right here. Just so think about it like this. I'm applying a 4 Newton force here. My friend is applying 3 newtons. Depending on where that force is going to be applied, my resultant, or like my final force, is going to change, right? If he applies it like 3 newtons up here, it's going to be one thing. If they apply it this way, it's going to be another thing. If they apply it this way, it's going to be another thing. So, logically speaking, where would you expect that maximum resultant to come? More likely than not, the maximum resultant is probably going to come when it is acting in the exact same direction as my initial forces, right? If I'm pushing the box this way, if my buddy comes and like pushes it in that same direction, then that's where you're going to get your maximum resultant, right? So really, your maximum resultant is going to come when 3 newtons is applied in the same direction. So what that means is 4 newtons plus 3 newtons, now a total of 7 newtons is pushing this way, so your maximum is going to be 7 newtons. That first answer is correct. B. The minimum magnitude of the resultant obtainable is 1 newton. Okay, so in which case, or like in what instance, would you expect the force, or like the pushing force, to be the lowest? If I'm pushing it 4 newtons this way, and like, you know, my friend wants to like stop me, where does he push from? They come to the other side, test. Okay. So basically, if my friend wants to stop me from pushing in this direction, rather than him coming and supporting me from this side, they will come from the other side and push it in this direction. So what that means is that they will apply 3 newtons in the opposite direction that I'm pushing it in. So what happens then? I'm applying 4 newtons this way, he's applying 3 newtons this way. The resultant is going to be 4 minus 3, which is 1 newton in this direction. So that resultant force will be 1 newton. C. The magnitude of the resultant obtainable is always 5. That's incorrect, right? Because we just determined that it can be 7, that it can be 1, depending on what the direction of the force is. So that third option is obviously wrong. So your first one's correct, your second one's correct, your third one is incorrect. Answer is option number 4. So that basically sums up like the discussion for physics 1. I'm pretty sure like that should be clear enough. This was mainly focused on like resultant force and like, to be honest, more like waves and optics than anything, which will be like a very big lesson if you decide to like pursue physics for A-levels as well. So yeah, good luck with your exams. Thank you.